Welcome to lecture 8 of module 4. We have been discussing in last series of lectures about the convective heat transfer and how to calculate the heat transfer correlations. Then we have seen the analogies. Now, today also we will be discussing again on convective heat transfer, but with a different topic. Here we will be discussing about that boundary layer heat transfer, and here we would like to see. So, boundary layer heat transfer, and we would like to see that the equations developed using the boundary layer concept or using the theoretical analysis and the boundary layer concept, we can find out the heat transfer correlations. So, this is another method. Solution of the equations of the boundary layer is another method of getting the values of heat transfer coefficients, or that is in term getting the value of amount of heat transfer or rate of heat transfer in case of convective heat transfer. Okay. Now, the question is, what happens when a fluid is flowing over a surface? Then what happens? A boundary layer develops, and this is because of the effect of the wall, because the wall tries to resist its flow and the fluid tries to move, and therefore, there is a gradient that of velocity that is developed across the flow direction. So, if I say it is like this, for a flat plate of this kind, say, so this is the flat plate of say some width is there in this direction, a flow is there in this direction. Say if I say that direction to be say x direction, along the x there is a flow, and that has been happening. So, what before it is entering into the leading edge, so this point is called to be leading edge. I will say that O, point O is becoming the leading edge. Okay. And if I say that these coordinates are like this x axis and this is say y axis, and then what is happening here is, before the fluid enters the surface, okay, there is an almost, and this is called an uniform flow across this cross section. If you see, this is the cross section. If you see at this point across the flow direction, there is an uniform velocity. Now, what happens as it enters into this onto the leading edge? Then there will be effect of the wall comes into picture, and this is related to fluid mechanics. I think you might have already got that exposure to this. And then what happens? There is a development of say a hypothetical boundary. It is not, there is no real boundary of this kind. This is called an hypothetical boundary, and we say that already we have partly discussed about this. So, this is the called laminar region, and we can say that there is another part. This is called laminar sublayer. This is called turbulent region. This part you can call it to be say buffer region, buffer zone, that we know that when there is a transition from a laminar zone to the turbulent zone, in between that zone is called the buffer zone. And we can say that, see, if this and if we consider up to this, so this region, okay, this region I will say as the transition zone, and this transition zone is that you can see is the behavioral change of the fluids. Okay. So, what is happening, as I was telling, that when there is a flow over the plate, I have taken a plate as an example, then what is happening? The wall of the plate is giving a resistance for the flow. It is trying to stop the fluid to go, and therefore, there will be resistance being placed, and so there will be a velocity variation. And we know that if I draw like this, so this is happening to be the velocity variation, and we can say that at this point, this is the point of no slip condition, where the velocity of the fluid particle which is adjacent or adhered to the surface of the wall is 0. Okay? That is called no slip condition. And as we go ahead, as we go along, then what is happening? That velocity is gradually increasing across, and then it is reaching some point. After that, there is no variation in the velocity, and we say that velocity in this region where there is no variation of velocity, that we will call as, say, V infinity is called free stream velocity. Free stream, already we have discussed several times, and this velocity is also a free stream velocity. Here also the effect of the wall was not there. Now here also, and here also we can say that the effect of the wall is not there. But as we go again in this direction, we can see that the velocity variation also in this region is changing. So this is called laminar region, then this is the turbulent region, and there is the transition zone. And as we understand that as we go along, the fluid behavior changes from laminar zone to the turbulent zone. So this is what is happening, and this hypothetical boundary, whatever I discussed, I told, this boundary is called the hydrodynamic boundary. Hydrodynamic boundary. Okay? And so this is also called hydrodynamic boundary or boundary layer. Hydrodynamic boundary layer. That means we can understand, we can define it like this, as if we consider, now it is looking like a single line, but actually this is the plate is there. So it is a layer of this kind. So this layer is becoming the hydrodynamic boundary layer. So, and in between there is always some kind of variation of the velocity, and what we say, the distance from the wall till the velocity variation at any location is called the boundary layer thickness. Let us call it to be delta, and this is a function of x, that we can understand that as we move along this. So these are the boundary layer thickness delta. You can say that this is the boundary layer thickness. The boundary layer thickness is gradually increasing as we go along this. Okay? So boundary layer thickness delta is a function of a Reynolds number. We can always say that with increase in velocity, Reynolds number increases. As Reynolds number increases, as the boundary layer thickness is also increases. And what we say that Reynolds number is defined in these particular cases is Rex. It is usually told this is called local Reynolds number, and it is x rho mu. X rho Vx infinity. Vx infinity, I will say that, say Vx infinity means the V infinity along x direction. Okay? So you can call it to be or Vx infinity. Okay? This is the flow of free stream velocity along x direction. So x rho Vx infinity by mu, or we can say that this is equal to x Vx infinity by nu. This is the momentum diffusivity. Now, as we discussed, these things we have already discussed little bit, and that we can say that there is a range of the Reynolds number Rex from 10 to the power 5 to 5 into 10 to the 5, below 10 to the 5 it is called laminar, and above 5 into 10 to the 5 which is called turbulent, and between 10 to the 5 to 5 into 10 to the 5 this is called to be the transition zone. That already we have discussed little bit. Now, exactly the similar concept can be applicable for heat transfer. So, when a fluid is flowing over a hot plate now if the plate is hot, then what will happen? There will be heat transfer from the plate to the fluid. So, that means we can expect, as we have seen analogically previously, that momentum diffusivity term is there. Similarly, we can have a thermal diffusivity term. So, if there is a thermal diffusivity term, so there could be again a kind of thermal transition, or there could be a layer where the temperature also can vary across the flow direction. So, when the temperature varies across the flow direction till a certain level, that is called a thermal boundary layer. Now, as we understand that when a fluid flow is there over a flat plate, then and the plate is hot. So, if we have a heat transfer along with fluid mechanics, fluid flow, then we can say that existence of both thermal and hydrodynamic boundary layer together. And if there is no heat transfer, only the existence of hydrodynamic boundary layer, and otherwise there will be an existence of thermal and hydrodynamic boundary layers. And then if we say that for any particular case, we can say that, so this is the leading edge. So, this is say a laminar flow. So, one it is, I will say that, say these are, I am sorry, okay. So, here it can be say, we can say that V x infinity, and this is say T infinity again. So, this is the free stream temperature. So, effect of temperature, when does it come on the fluid, that is called free stream temperature. And we can say suppose this is a thermal boundary layer, and this I will say that hydrodynamic boundary layer, Now, the question is, here it is along x direction, and at this point velocity V x equal to 0, that is, and we will say that T w is the wall temperature, and we can say that T w is greater than T infinity. So, heat is being transported from the wall to the fluid. Now, what happens that is it that always this thermal boundary layer will be below the above the hydrodynamic layer? It is not necessarily like that. It depends upon the parameter that is called diffusivity. So, we can have situations where thermal, we will see later also that thermal boundary layer can be coincident with the hydrodynamic boundary layer. Thermal boundary layer can be equal to the thermal boundary layer can be coinciding with the hydrodynamic boundary layer. Hydrodynamic boundary layer can be below the thermal boundary layer, or thermal boundary layer can be below the hydrodynamic boundary layer. It depends upon the relative values of the diffusivities, thermal diffusivity and momentum diffusivities. So, we can say that we know that Prandtl number is equal to nu by alpha. So, it is a ratio of two diffusivity, that is momentum diffusivity by thermal diffusivity. So, we can say that it is, we will see also later on that if Prandtl equals to 1, then nu is equal to alpha. So, both the diffusivity terms are same. Then we can always say that the two boundary layers will be coinciding with each other. Now, I will tell, as I said that there is a boundary layer thickness for hydrodynamic boundary layer thickness, then there can be a thermal boundary layer thickness also, delta T. So, I will define delta T as thermal boundary layer thickness. So, it is nothing but the distance from the wall till the boundary layer where the effect of wall is observed, that means that variation of temperature is being observed. Okay. Therefore, delta T is called thermal boundary layer thickness, and delta T is also a function of x. As we go along, the delta T also changes. Now, so when Prandtl number is equal to 1, nu equal to alpha, then delta is equal to delta T, and that means that thermal and hydrodynamic boundary layers coincide. With each other. Now, another case that if Prandtl is equal to say less than 1, if Prandtl less than 1 means nu is less than alpha, and then if nu is less than alpha, then we will get delta less than delta T. If delta less than delta T, that means hydrodynamic boundary layer will be below the thermal boundary layer. So, hydrodynamic, now if I say is that hydrodynamic boundary layer as HBL is below TBL, thermal boundary layer, and if Prandtl is greater than 1, that means nu is greater than alpha, okay, and then delta is greater than delta t, or HBL is above TBL. And we know that we get Prandtl much less than 1 for liquid metals, already we have discussed previously, and Prandtl much greater than 1 for polymeric fluids, non-Newtonian fluids. Okay. Now, question is that this is the brief about the hydrodynamic and thermal boundary layers. Now, if I have to know that how to go for finding out the heat transfer coefficient or rate of heat transfer in case of a boundary layer flow. So, taking a flat plate as an example, we can just do some mathematical development and then find out, with the solution of that we can find out how the H value to be calculated. So, to go ahead for that, what we will do is we will see that how to develop the mathematical expressions, mathematical equations applicable for boundary layers. So, as we know, when heat transfer with flow is involved, then both we have to consider that hydrodynamic boundary layer, we have to consider the thermal boundary layer together. When only fluid mechanics is involved, only hydrodynamic calculations is fine, but when heat transfer is associated with fluid flow, that means simultaneous heat and momentum transport. Okay. Under that situation, we have to make use of both hydrodynamic equations as well as thermal energy equations. That is what we are going to do. Now, consider typically, so this is, as I show, this is the y direction and a typical boundary layer. So, what we will do is, this is x direction and I will take a small differential element. So, this is the cell balance approach we will do, and what are the things we are going to study now. First, for hydrodynamic condition, so we have to find out that governing equations for hydrodynamic boundary layer. Equations for hydrodynamic boundary layer that will be developed. Okay. And what we will do, we will develop a continuity equation and we will make use of momentum equation. Momentum balance, or rather equation of motion, which is nothing but momentum balance equation. Okay. Now, what we will do, consider, so we are enlarging this view. So, let us say that this is dx and this is dy. So, it is a differential element. Now, I am writing here in the enlarged form of the differential element, and let us see what is what. So, say this is x directional velocity Vx and the pressure in this direction is P and into area. So, we have taken width equal to 1 unit width. So, the area will be in this direction, the area will be dy into 1, this is dy into 1 unit width. Okay. So, I will write this one as dy and say this one as I will write as dx. So, dy into 1 will be the area from this side and dx into 1 will be the area from that side. Okay. So, P into dy, that is the pressure is force per unit area. So, pressure into that dy into 1 is the area. So, that gives the total pressure that is acting on this side. Okay. And then in the right hand side it will be Vx plus del Vx by del x into dx. Okay. That will be the velocity here, and pressure will be P plus del P by del x into dx into dy, that is the pressure force. So, this is the pressure force, this is the velocity, okay, and that is entering in along x direction in this and is going along this direction, and now velocity from the bottom, that is entering into this layer. So, momentum, what is the momentum transport here? Actually, we understand that higher fluid at the higher layer will have a higher velocity than the fluid in the lower layer. So, there is a momentum transport across, so there is a velocity gradient, that means the fluid of higher layer is coming to the lower layer, and lower layer fluid can go to the higher layer. When lower layer fluid go to the higher layer, then what is happening? The higher layer momentum is reduced, and higher layer fluid is coming to the lower layer, then lower layer momentum is increased. So, this is the thing that is going to happen here. So, we will write like this, that as if that this is the lower layer fluid that is entering. So, it is basically V y, that is the is entering with the velocity V y at that point y, and here we will have a frictional force that is acting, that is the viscous force that will act against the flow direction. So, this is the flow direction, this layer is flowing in this direction. So, this is the viscous force that will act in this direction, and this is equal to mu into dx, I am sorry, it goes by Newton's law of viscosity basically. So, mu into we will write del Vx by del y into dx, that is what is the frictional force. And now, when this velocity comes up, then its value becomes okay. And this, when the velocity and the top point will become like this. So, V y plus del V y by del x, sorry, del y into dy, and that. So, here it will be the acting in this direction, because it will go like this. So, it is the shear force. Okay. So, this is actually your mu into del V x by del y, the gradient, plus del y of del V x by del y into dy, and then whole multiplied by dx, sorry, into dy whole multiplied by dx. So, this is what is becoming that. Okay. So, these are the entry and exits. Now, at steady state, now if I go for the mass balance at steady state. So, mass balance is giving us the continuity equation, and total entering would be equal to the total things going out. So, mass entering, I will write total mass entering. So, from there if we write, then from the mass balance at steady state, that is equal to rho V x into dy, that is entering from this side, plus rho V y into dx, that is entering from the bottom side. What is this? This is the mass, because V x is the velocity, dy in the. So, this is what is to be said. Now, V x is the velocity. Now, velocity into the area will be the volumetric flow rate. So, area is dy, in this case area is dy, in this case area is dx, dx into 1 is the unit width. So, dx dy into like this, if you consider this. So, dy into 1 is that like this will be the area. So, dy into 1 will be the area through which the velocity Vx moving. So, dy into 1 is the volumetric flow rate. Volumetric flow rate means meter cube per second or meter cube per time. So, a volume flow per time, and rho is the density, rho is becoming the mass flow rate. So, this is the mass flow rate actually. Rho Vx into dy will be equal to rho Vy into dx, and that these are the two entering from two sides, and what is going out is basically this rho Vx plus del Vx by del x into dx plus into dy, this will be multiplied by this dy is the area, and plus rho into Vy plus del Vy by del y into dy into dx. Okay. Now, from this we can write as that del Vx by del x plus del Vy by del y equals to 0. So, basically in two dimensional term we can say it is this. So, we know that volumetric continuity of equations as grad dot v equals in fluid mechanics, we have studied this. What does it say? It is del Vx by del x plus del Vy by del y plus del Vz by del z equal to 0. In the present case this is not there. So, therefore, these two are matching. So, this is what is the continuity equation that we could develop from there, which is basically a fluid mechanics. Now, if we see that momentum balance equation of motion. So, what is equation of motion? It is based on the Newton's second law. So, Newton's second law of motion says, what it says that application of force will generate rate of change of momentum. That is what the Newton's second law, and that is what we will be doing. So, we have already seen in the previous diagram that what are the forces being applied, that is the pressure force and the viscous force, these are applied, and we will have also seen that what will be the rate of change of the momentum, because we know the velocity terms, then we will find out what is the change in the momentum. So, that is what if we try to do, then doing the momentum balance. So, what we are doing is momentum entering at left face, and this is equal to will be equal to rho Vx, that is the mass, into Vx, okay, m into velocity, mass into velocity is nothing but the momentum, and into the dy, that is what they are, dy into 1 is the area. So, this is the momentum which is entering at the left face, momentum leaving at right face. So, if I see this figure again, this is the left face, this is the right face, this is the bottom face, this is the top face. Okay. So, then that will be equal to, we will write like this, rho into Vx plus del Vx by del x into dx, and this is the whole square. This is the one part is the mass, and then and multiplied with the same velocity will become the momentum into dy. Similarly, momentum entering at the bottom place. At the bottom face, okay, at the bottom face is equal to rho Vy is the mass that is entered, and it is entered with a velocity, and it is reaching to this region of x directional velocity. So, this is this into Vx into dx, okay, that is becoming the momentum, and then this is the x directional momentum. Okay. So, I can say that x directional momentum, okay, entering, and then x directional, that is why the Vx is multiplied. V rho into Vy is becoming a mass, multiplied by Vx is the x directional momentum. X directional momentum leaving the top face, and that will be equal to rho into whatever is del Vy y by del y into dy, that is the mass that is entering, and then it is leaving with a vector velocity Vx into this. So, it will be Vx plus del Vx by del y into dy, and then we have to multiply by again the dx. So, this happens to be this. Now, if we do, and then we have already seen the applied forces. From the left hand side there is the pressure force, and from the right hand side there is another pressure force that will act, and also that the viscous forces. So, if we apply applied forces will be equal to rate of change of momentum. If we apply that logic, and then we will say that mu into del square Vx by del y square into dx dy minus del p by del x into dx dy. Okay. So, this is becoming the total viscous force, this is becoming the total pressure force. How it is coming? This is basically from like this, P into dy minus P plus del P by del x. This is from here, del P by del x into dx into dy. So, this says equal to minus del P by del x into dx into dy. This is this term, okay. And then another part is minus mu into del Vx by del y into dx plus mu into, because the in this case as we have seen that in the pressure acts in this direction, here the pressure acts in this direction, here the viscous force. That is why I am some negative x, and here the viscous force acting in this direction positive x. So, we are writing mu into del Vx by del x into dx plus mu into del Vx by del y plus del y of del Vx by del y into dy and into say dx. So, then if we, so these are the this part is finally giving you mu into del square Vx by del y square into dx by dx into dy. So, this term is nothing but this term that we are getting. So, now, so this is the applied force along x direction, and we have to get the rate of change of momentum in the other direction. So, rate of change of momentum is if we add up all the things and then find out, it will become rho into Vx plus del Vx by del y, sorry, del Vx by del x whole square into dy minus rho Vx square dy, that is the x directional momentum, and then from y direction whatever is coming, plus rho into Vy plus del Vy by del y into dy into Vx plus del Vx by del y into dy into dx minus rho Vx square into dx. I am sorry, rho Vx into Vy into dx. That if you see these here, you get that here. What is that? Yes, rho Vy Vx into dx. Now, then we finally get, if we do this, then we finally get by neglecting the second order differentials, second degree differentials, higher so we get rho into Vx del Vx by del x plus Vy into del Vx by del y equals to mu into del square Vx by del y square minus del P by del x. So, this says now this implies that Vx into del Vx by del x plus Vy into del Vx by del y is equal to nu into del square Vx by del y square minus 1 by rho into del P by del x. Now, for constant pressure flow, situation, del P by del x equal to 0, then Vx del Vx by del x plus Vy del Vx by del y is equal to nu into del square Vx by del y square. So, this becomes the basic this becomes the governing equation. So, it is similar to, in case of fluid mechanics we have studied, similar to Navier-Stokes equation, where in Cartesian coordinates for two-dimensional system exactly the similar kind of, for x directional velocity, if we see the Navier-Stokes equation, we will get the same thing, okay, and where the gravity is neglected and all. Okay. So, if we write the Navier-Stokes equation, the vectorial form of Navier-Stokes equation is rho dv by dt is equal to rho g minus grad p plus mu into grad square v. That is what for x direction momentum at steady state when del Vx by del t equals to 0, rho into Vx into del Vx by del x plus Vy into del Vx by del y plus Vz into del Vx by del z, okay, is becoming rho Gx minus del p by del x plus mu into del square Vx by del x square plus del square Vx by del y square plus del square Vx by del z square. That is what. And in this case, as we know that there is no velocity along z direction, and it is a horizontal plate is assumed to be horizontal plate, okay, horizontal flow, and del p by del x is the constant pressure flow. Okay, and this is if p is constant, then del Vx by del x is constant, okay, and then this is also 0, so no variation in z along z direction. Then what we get finally, rho into, or say exactly the same expression that what we have developed. So, Vx into del Vx by del x plus Vy into del Vx by del y equals to mu into del square Vx by del y square. So, somebody can make use of the Navier-Stokes equation to come down to the expression, and or otherwise it can be obtained from the simple what is that called, cell balance approach. Okay. Now, we have got two equations, one is called momentum balance, one is called continuity equations. Now, this there is a solution procedure to this. Blasius has given a solution to this, to the above equations, numerically. So, before giving the solution, so he had approached that there are some what should I say, changes, some modifications, or say some calculations or developments rather, that is made by Blasius, and according to what he has said, that he has defined two variables. What are these? That eta is one variable, is called its y by delta, that is a function of x, and he said that Vx by Vx infinity is equal to phi into eta, phi is a function of eta, and then he defined a stream function. Okay. Let us define a stream function psi such that V x is equal to del psi by del y, and V y is equal to minus del psi by del x, where psi satisfies the continuity equation. Okay. Now, under that situation, psi is equal to nu into x V x infinity whole to the power half into f of eta, and where eta equals to y by nu into x by V x infinity whole to the power half, and nu is mu by rho, and x is the momentum density, x is the distance from the leading edge over the boundary plane. So, what we get from here is V x is equal to del psi by del y, and that is equal to del psi by del eta into del eta by del y. So, doing the differentiations, it can be obtained as V x infinity into d f by d eta. So, because f is function of eta only, and which is nothing but V x infinity into f dashed. Okay. And then V y equals to yes. So, phi y is equal to minus del psi by del x, and that is equal to minus del psi by del eta into del eta by del x. So, one can do this and then find out this is equal to half of V x infinity nu by x to the power half, okay, and then eta into df by d eta minus f, like this. And then, so if we do further differentiation, then we get del V x by del x is equal to minus V x infinity by 2 x into eta into d 2 f by d eta 2, and then del V x by del y. Because why we are doing this? We have to put these values to that equation, momentum balance equation. So, this is equal to V x infinity square by nu into x into d cube f by d eta cube. So, by doing all this, when we put all the values, then we finally get half of f d 2 f by d eta square plus d cube f by d eta cube equals to 0. And boundary conditions are y equals to 0, that means eta equals to 0, V x equals to 0, that is d f by d eta equals to f dash equal to 0. And another condition is y equal to 0 implies eta equals to 0, then phi y equal to 0, that is eta into df by d eta minus f equal to 0, which implies f equals to 0. And then at y is equal to at y tends to infinity, eta tends to infinity, and then V x is equal to V x infinity. So, here we can understand y tends to infinity means y is near the thermal boundary layer, end of the is y equals to close to the thermal boundary layer thickness, then V x is becoming V x infinity, and that is d f by d eta is equal to f dash is equal to 1. So, these are the boundary conditions. Applying these boundary conditions and follow these equations, for this equation and applying these boundary condition, then numerically Blasius solved numerically to get V x by V infinity versus eta values. Okay. And then what he has done? He has generated the values in the form of tables, as well as here what he has given eta, then f dash, f double dash, for different values of eta. He has generated the value. This is the table of Blasius, and he has given a plot also. The plot says that this is the eta, and here it is say Vx by Vx infinity, okay, and this Vx by V maximum value will be equal to 1, and he says that this value is like this. So, this is the, so this is, you can say that this is the 99%. When the value is 99%, or if I say this, say 0.99, and that is happening say at eta is equal to say 5.0. So, they say that according to his plot of Vx by infinity versus eta, and also in the table the same value is given in the table. So, this is, or this is nothing but f dash. So, here for eta is equal to 5.0, its value is 0.9915 f dash. So, we can find out this is the value. So, according to the numerical solution and the data provided by Blasius, we can say that delta is equal to 5 or rather we can say that eta is equal to delta into v in x infinity by nu into x whole to the power half, and that is equal to 5.0. We have seen that eta is equal to 0, and eta expression is eta is equal to basically y into v x infinity by nu x whole to the power half, and here y is equal to delta. Okay. And then we can find out that delta is equal to 5.0 by nu into x by v x infinity whole to the power half, and this is equal to 5.0 x into r e x to the power minus half, or delta by x is equal to 5.0 into r e x to the power minus half. Now, if we see here previously that definition of eta, eta is equal to y by this, I am sorry. So, here in this what we will write is this to the power half into delta. So, here it should be like this into y, and y is equal to delta here. So, delta by x is equal to 5.0 into Reynolds to the power minus half, and then from there if we try to see that friction at frictional drag tau wall is equal to mu into del V x by del y at y equals to 0, and this is equal to V x infinity into V x infinity by nu x whole to the power half into f double dot 0, and then from the values provided it happens to be 0.332 mu V x infinity into V x infinity by nu x whole to the power half, and this is actually is equal to 0.332 rho V x infinity square r e x to the power minus half. Okay. So, r e x is nothing but the r e x is local Reynolds number, and that is x V x infinity by nu. Okay. Now, for the whole plate, okay, for the whole plate average R E L is equal to plate Reynolds number and this is equal to L V x infinity by nu, and then F D total drag that is equal to 0 to L tau w dx, and if we put here tau w is equal to this and do the integration, this becomes 0.664. Already we have discussed a little bit on that. Mu v infinity into REL to the power minus half. Okay. And then CD is the drag coefficient is equal to FD by area into half rho Vx infinity square. So, this CD is the drag force by inertial force. So, FD by area is the force per unit area, and this half rho Vx infinity square is the inertial force per unit area. So, if we put these values, it becomes 1.328 into REL to the power minus half. Okay. So, this way we can find out that at least from this expression or by this analysis, we are able to find out that what is that shear force, what is the wall shear force, and what is the drag coefficient, and how the momentum is transported. And exactly similar analysis we have to do to so we have got the expression for velocity, and now we have to find out the expression for T bar or heat transfer coefficient, and we will be finding out that in terms of Nusselt number. So, here we have found out that wall drag, similarly will be found, or wall momentum, we can say that the tau W is nothing but the momentum transport. So, we have found out the momentum transport at the wall. Similarly, when we go for the energy balance equation, there we will be finding out the momentum transport energy balance equation, there we will be finding out the heat transport at the wall. So, heat flux at the wall, that will be found out in terms of Q, and then once we find out the values of Q, from there we can find out the values of Nusselt number, and once we know the Nusselt number, we can find out the values of heat transfer coefficient to calculate the value of rate of heat transfer. Maybe we will discuss this part in the next class. To discuss that, what we have to do is, as we have taken that momentum equation in case of heat transfer, then we have to consider the thermal boundary layer, and we have to take into account that energy equation. So, that part we will be discussing in the next class to see that how this can be taken into account. Now, what we will discuss is, we will take up a problem which is related to the hydrodynamic boundary layer that is being happening. Consider the problem. A flat plate 2 meter by 1 meter at 155 degree centigrade is placed, okay, in an air stream flowing at 10 meter per second velocity. The air pressure is 1 atmosphere and bulk temperature is 25 degree centigrade. Then determine the local heat transfer coefficients and B, the average heat transfer coefficient, and C, the, so here its coefficients, the rate of heat loss from the surface. So, what we can say in case of, this is a flow over a flat plate, it is a boundary layer flow and heat transfer is taking place. Now, what we have already discussed the correlations in previously in some sections of our discussions. We have I think we have discussed in somewhere in lecture 5 of module 4 we have discussed, okay, this partly. So, fluid properties at TA, film temperature, and that should be 155 plus 25 by 2 is equal to 90 degree centigrade, and we can say that rho F is equal to 0.962 kg per meter cube, then mu F is equal to 2.13 into 10 to the power minus 5 kg per meter per second. Kf is equal to 0.031 watt per meter per degree centigrade. Cpf is equal to 1.01 kilojoule per kg per degree centigrade. Okay, and then Prandtl F is becoming mu Cp by K. If we put the values, it is becoming 0.694. So then Re d max, Re is equal to REL is based on the length, total length, that is the maximum Reynolds number, is equal to L V infinity rho by mu, and that is equal to 2 into 10 is the 2 meter, okay, into V is equal to 10 meter, V into 0.962 dV rho by L V rho by mu, 2.131 into 10 to the power minus 5, and this is equal to 9.03 into 10 to the power 5. Okay, so this says from here you can say that V infinity rho by mu is equal to 4.515 into 10 to the power 5. Now, what you can see here, that the velocity is 9.03 into 10 to the power 5. What? So, it is at the end of the, so if you consider this, so like this, there is a flow and is like this, and here at some point at this L, it is 9.03 into 10 to the power 5. So, there will be some point here why it is laminar. So, we have to find out that x. So, to find out the location for laminar flow to be valid, we know that 5 into say 10 to the power 5 will take into account that is say 5 into 10 to the power 5 till that is the laminar, and then afterwards the turbulence. So, this is equal to, so say LC critical into V infinity rho by mu. From there we have seen V infinity rho by mu is equal to something. So, we can get LC is equal to 1.107 meter. So, for 1.107 meter it is laminar, and this is rest of the thing it is turbulent. So, what we can say that H L x by k Nusselt number laminar region is equal to 0.332 into x V infinity rho by mu whole to the power half into Prandtl to the power 1/3. This relation we will be discussing again in the next class, that we will be getting this relationship from the boundary layer analysis. Already we have seen this in our as I told you in lecture 5 of module 4. Lecture 5 of module 4 we have discussed this. So, then we can find out from here HL as 6.12 into x to the power minus half, and for turbulent region we will use a different equation, that we will use that H turbulent into x by k is equal to 0.0296 into x V infinity rho, that is the Reynolds number to the power 4 by 5. This already we have told, into Prandtl to the power 1/3. If we put all these values, then Ht is becoming 27.13 into x to the power minus 1 by 5. So, then we got these expressions for this heat transfer coefficient in the laminar and turbulent regions. Then average is equal to H average is equal to half of 1.107, then 6.12 x to the power minus half dx plus 1.1072 to 27.13 x to the power 15 dx. So, this gives me the average H value, and this, if we do the integration on all these things, we will get it to be 17.57 watt per meter square per degree centigrade. And then the rate of heat loss is equal to Q is equal to H bar area into delta T, and that is equal to H bar is equal to 17.51 into area is 2 into 1 into delta T is equal to T w minus T infinity, and that is 155 minus 25, and this gives you 4568 watt. So, that is equal to 4.568 kilowatt. So, what actually is the motto of this problem I wanted to tell is that in the problem we have been given a data, and what we are seeing that with the help of the data we have found out the Reynolds number, and the Reynolds number is found to be 9.03 in 10 to the power 5. Okay. And then for that Reynolds number, it is lying in the transition is turbulent region, is more than 5 into 10 to the power 5. So, what we will see is that how to what extent of the length it is in laminar region, and to what extent of the length it is in the turbulent region. So, to find out that, what we have done is, in the next part what we have calculated, that we have assumed that till 5 into 10 to the power 5 is the laminar region, and then afterwards is the turbulent. So, we have found out the length 1.107 would be the length till which it will be in laminar region, and then afterwards it will be the turbulent region. So, for laminar region we have this is the relationship that already we have discussed, that correlation. If we apply these correlations, we will get an expression of H L which is a function of x, and then again in the turbulent region this is the correlations that we apply, then this is H T you will be getting as 27.13 x to the minus 1 by 5, that is another correlations. Now, these two correlations are applicable to different lengths. It is first one is 0 to 1.107, and the second one is 1.107 to 2. So, now if you do the integration and then take an arithmetic mean of that is giving us the average value of heat transfer coefficient, and from the average value, once we know, we can find out what is the heat loss from the bulk. So, that is what is giving you that idea about that how to calculate this heat transfer behavior in the turbulent flow. But however, what we have yet to do because of the lack of time, what we could not do is that we will find out the relationship that Nusselt number is a function of Reynolds number, whatever we have applied for laminar region 0.332 into Nusselt number is equal to 0.332 into Reynolds to the power. If you see that Reynolds to the power half and Prandtl to the power 1/3, we will see in the next class, next lecture with the help of energy balance equations. Thank you.